All right, we are here to look through and go through all the questions on this August 22 Regents Chemistry exam. All right, so these are the guidelines about electronics. Here's part A, the first multiple choice section, where the question should be the easiest for multiple choice. Obviously, use the reference tables as you need them. Now, it says, what is the number of protons in an atom with the electron configuration of 2-5? Well, I know this answer right away, but I'm going to show you how to find it quite simply. So go to the periodic table, find the element that has the electron configuration, right? Here's electron configuration, and it is right here, okay? You can see that the atomic number is 7, and remember, atomic number defines the number of protons in an atom. So that is going to be 4. Also, you could have simply added 2 plus 5 and got 7. In the wave mechanical model of the atom, so this is the modern model of the atom, an orbital, this is just a definition question. You should know that it is the most probable location, most probable location of finding an electron. Okay. In the ground state, which shell of a potassium atom has an electron with the greatest amount of energy? All right, so when you have a nucleus and then you have electron shells around the nucleus, you should know that the shell closest to the nucleus has the least amount of energy, and the shell furthest from the nucleus has the most energy. So let's look up potassium. Potassium is K. If you don't know it, remember you have table S here if you panic. And let's look at its electron configuration again. We have 2, which means 2 electrons in energy level number 1, 8 electrons in energy level number 2, 8 electrons in energy level 3, and 1 electron in energy level 4. So which one has the greatest amount of energy? The one in the 4th energy level, because it is furthest from the nucleus. Which phrase describes 2 atoms that contain the same number of protons but a different number of neutrons? This is a definition question asked almost every year in some way. It is isotopes. That's the definition of isotopes. So an example would be, carbon 13 and carbon 14. Same element, so they have the same number of protons, but a different number of neutrons. All atoms of the same element have the same what? They have the same number of protons. That's literally how you define an element, right? So atomic number, number of protons, all atoms of the same element must have the same number of protons. Which group 15 element is classified as a metal? Okay, so I'm going to need to look at the periodic table. Groups go this way, right, up and down, vertically. Here's group 15. So we have first nitrogen, nonmetal. Second, phosphorus, nonmetal. Arsenic, metalloid, touching the staircase. Antimony, metalloid, touching the staircase. So there we go, bismuth. And there we go. Okay, so that's the one that's the metal. Compared to the number of electron shells and radius of an aluminum atom in ground state, a boron atom. So I'm going to need to compare the two. So I'm going to have aluminum and boron. Okay, so what do I notice? Do they have the same number of electron shells? No, boron has 2 electron shells and aluminum has 3. So compared to the radius and electron shells of an aluminum atom, boron has, first of all, it has less electron shells. So let's cross out more. If it has less electron shells, what should it have? I mean, think logically, right? It should have a smaller radius. Hydrogen sulfide is classified as a, well, it is simply just a compound. When we have a chemical formula, it doesn't say aqueous. Aqueous would be a mixture, but compounds always have atoms in a fixed proportion. Proportions that vary is a mixture, so they're trying to catch you on that one. All right. Number 9, a structural formula differs from a molecular formula in that a structural formula literally shows you how the atoms are arranged. So a structural formula would be C, with the lines for H's, versus the molecular formula is just like this. It tells you what's there. The molecular shows you literally how they're arranged. Which type of reaction occurs when a compound is separated into its element? So when you break it apart, what is that called? Decomposition, when you break it down. Which term represents two categories of compounds? Okay, so it was either going to be, for this question, it's going to be ionic or covalent, or ionic and molecular. Molecular and covalent are the same thing. So remember this, that molecular equals covalent. Okay, so the two kinds of compounds are going to be ionic and molecular, or ionic and covalent, depending on how the question is asked. When an atom of hydrogen and an atom of chlorine combine to form a molecule of hydrogen chloride. So what it's saying is when this happens, hydrogen plus chlorine, again, drawing a picture, writing something down is going to be helpful. All right, so they're saying this happens. Well, first of all, what you should realize is happening is that a bond is forming, all right, which allows me to get rid of broken. Right? Now, think about this. This is the one where you have to, at least for me, I think in reverse. When I have to break a bond, it takes energy. So when I form a bond, it releases energy. Okay, so the opposite. So forming is going to release energy. All atoms of the element vanadium must have the same, oh my goodness, this is almost same as other questions. So if it's the same element, it has to have the same what? Atomic number. That's it. That's the end of the story. That's what they have the same. Which sample of matter can be separated into two different substances by physical means? So what they're asking you for in this case is which one is a mixture, because mixtures can be separated by physical means. Well, they're testing to see if you remember that aqueous means what? Aqueous means dissolved in water. And if it's dissolved in water, it is a mixture. Okay? Two liquids can be separated by distillation. Okay, what is distillation? Well, that's when you boil to the lower boiling point, allow a substance to evaporate, to vaporize, cool, condense, collect it. So it's based on their differences in boiling point. That's just a question you should know. Distillation separates based on boiling point. Which unit can be used to express the concentration? So I know the answer right away, but this is a reference table answer. So you go here to table D and you look down for concentration, and there are two options, parts per million and molarity. So go back here and parts per million. Compared to the freezing point and boiling point of water at 1 atmosphere, a 0.5 molar aqueous solution of sodium chloride at 1 atmosphere has. Well, if you remember this, so boiling point is a high number, or at least higher number, right? And freezing point, again, it's going to depend on the substance, is lower. So what happens when you add something to water, the boiling point gets even higher and the freezing point gets even lower. So compared to water, the solution will have a lower freezing point and a higher boiling point. Which form of energy is converted to thermal energy when propane burns in air? Well, what you do is you take the energy in those chemical bonds. Chemical energy is from bonds. So you take the bonds, break them, and then you convert it to a different type of energy. According to the kinetic molecular theory, which statement explains why an ideal gas can be compressed into a smaller volume? Well, because in an ideal gas, the particles are super far apart. So if an ideal gas has particles that are super far apart, they absolutely can be squished together in a smaller space. Okay? Under which conditions of temperature and pressure does a sample of propane behave least like an ideal gas? Okay, so for an ideal gas, what do we need? Okay, so let's talk about that first. So for ideal gas, we need high temperature because those particles have to be moving fast. And we need low pressure because they need to be far apart. So we don't want them squished together. But if we are looking for least like an ideal gas, we want the reverse. So we want low temperature, right? And we want high pressure. So let's look through our answers. And I went low temperature, so get rid of the high temperature, right? And we want high pressure. So do you see it? It is going to be this one, okay? Compared to a 1.0 liter sample of carbon dioxide gas in a sealed rigid container at STP, a 1.0 liter sample of methane gas in a sealed rigid container at STP. This is Avogadro's law. You just got to know it. They have the same number of molecules. That's it. A chemical reaction occurs when what? A chemical reaction occurs when the chemical formula changes. So let's see. Started with this, ended with the same formula. Started with this, ended with the same formula. Started with this, ended with the same formula. Well, there we go. Look at this one. Started with O2, ended with O3. The chemical formula changed, so it is a chemical reaction. What is the purpose of adding a catalyst to a chemical reaction? Well, we are providing an alternate pathway that requires less activation energy. Okay? Okay, systems in nature tend to undergo changes toward, well, you should know this, less energy and greater disorder, just like everybody. Your life just gets more chaotic and you'd like it to happen with less effort. Which reaction occurs at the anode in an electrochemical cell? So we have a couple phrases to help you remember this. Anox, which means anode oxidation. Red cat, reduction at the cathode. So what occurs at the anode? Well, that is oxidation. As more NaCl solid is dissolved in a dilute unsaturated NaCl aqueous solution, the conductivity of the solution, well, what happens? If you add more, you get more ions, and the conductivity is going to increase. Which substance always forms when an areneous acid reacts with an areneous base? So let's see, do you remember this? The equation for neutralization is acid plus base yields water plus salt. The salt depends on what acid you had and what base you had. So what's always there? That would be water. All right. Which symbol represents a nuclear emission with the greatest mass and the greatest ionizing power? Okay, so let's go to reference table. Which one are we going to look at? We're going to look at table O. So let's get all the way to table O. Top number represents mass. Bottom number represents charge or atomic number if it is an element. So the greatest mass, the biggest number on top, you can scan through this table, but it's right here. It's alpha particle. So right here, alpha particle. One benefit of a nuclear fusion reaction, what is it? Well, it gives us a huge amount of energy, and it does not produce the same radioactive wastes. Fission, huge amount of waste, but that wouldn't be a benefit, right? Determining the age of a wooden beam from a sunken ship is an example of a beneficial use of radioactive nuclides. So which ones should you know? So iodine 131, that is for our thyroid. Uranium, that is for rocks and minerals. Okay. Carbon, that's for dating once living things like bones, people, trees. Okay. What else do we have? Polonium. We have technetium, a few others, but these three are kind of the big ones that you should remember. And now we finished part A. All right, we are moving on to B1. This is the second section of multiple choice questions. So these may be a little bit more complicated and involve a little bit deeper thinking. Okay, so we see we have a bright line spectra. It says there is a mixture formed from two of these elements. Here we have it down here. And our question says, which two elements are present in the mixture? All right, so the way we have to go about this, all right, is to look at each individual element. And in order for the element to be present in the mixture, all of the lines must be present. All right. So I'm going to pick outliers. So do you see how I have this line out here? When I go down, is absolutely missing, right? It's not here. So that means I eliminate E as an option. Okay. What else? So do I see any others that are obvious? Ooh, look right here. See this? I have two banded together and they should be right here, right? But they're not. So that means I can eliminate G, which means I have just now found which two elements are present in my mixture. And it is A and Q. What is the approximate mass of an atom that has these particles? What should you know? Okay, so a proton has a mass of 1 U. A neutron has a mass of 1 U. An electron has a mass of 0 U. Well, technically not 0, but around 1/2000th, so we just don't include it in the process. So what do I have? I have 10 protons and 9 neutrons, so that would be 19 U. Which electron configuration represents the electrons of an atom in an excited state? So it doesn't tell me what atom. So what you could do for this question, turn it just into a reference table question and look and see which ones you see on the periodic table and which ones you don't. So when I start looking through, I'm going to look for something that I don't see here. And I see 2881, that's potassium. So let's get rid of that one. And I see 282, that's magnesium. All right, so let's cross that one out. Now I'm down to these two options, okay? And this one required one extra level. So do you see how this one is a 9? Let's look through the periodic table. Do we ever see a 9? Yes, we do. So do we see a 2892? So look at this right here, 2892. Well, so that means that is scandium. So we can cross this one out, which means that what? This absolutely has to be the right answer. So it was a reference table question. Double check your work. Given the information about the naturally occurring isotopes of bromine, so here we have some data, which numerical setup can be used to determine the atomic mass? So notice that the abundance is in percent. What does that mean? That means at some point I have to divide by 100. Okay, I have to divide by 100 because in order to do math with percent, that's what I have to do. So you can see in this first option right here, I did not divide at all by 100. I'm just multiplying, right? The number straight, that's definitely wrong. This next one, I'm not dividing by 100, but look what is done. Do you see how this is 0.4931? So what I did was I took that decimal and I moved it over 2 places, which literally is dividing by 100. So here all I have to make sure is that I pair the correct atomic mass with the correct abundance. And so our answer is going to be this one. What is a chemical name of the compound CuS? Okay, well, it is only 2 elements. When it is 2 elements, we should end in IDE. So, okay. What is sulfate? If you don't remember what sulfate is, you can look at table E really quickly and see that sulfate looks like this. And that's definitely not what we had in our formula. So let's look up sulfur. When sulfur is the second element, it's going to need that negative charge. So that's going to be -2, right? So if sulfur, the sulfide ion, has a -2 charge, in order to make that compound balance and have an overall charge of 0, copper would also have to have a +2 charge. Given this equation, what is the mass of N2 produced when 1.0 grams of H2 completely reacts with 15 grams of NO to produce? Okay, this question is really not as hard as it might seem. So what do I have? It says that I have 1.0 grams of H2, right? And I have 15.0 grams of NO, and I produce how much nitrogen? And I produce 9.0 grams of this. All right, let's just move it down a little bit. Okay, so conservation of mass means if I start with 1 gram, I end with 1 gram, okay? But I'm not starting with 1, right? I'm starting with this. 1 plus 15 is 16. So on the other side, I also have to have 16 grams. So what is the missing number of grams? Obviously, it is 7, okay? An atom of which element bonds with an atom of hydrogen to form the most polar bond? Okay, so what that means, if it is the most polar, okay, it will have the greatest electronegativity difference. All right, so I need to look up the electronegativity values. Okay, so let's look them up. Where do we go? Table S. So hydrogen is 2.2. Okay, so we'll write that for hydrogen because that's the math for all of them. So we need bromine, chlorine, fluorine, and iodine. All right, so fluorine electronegativity is 4.0. Bromine, chlorine, iodine, right? Chlorine is 3.2. And we need bromine and iodine left, right? So bromine is 3.0. And then iodine, okay, is 2.7. All right, now you can do all the subtraction or realize the way to get the biggest difference is to start with a bigger number, right? So it is going to be fluorine, all right? Given this diagram representing a classification of matter, which types of matter are represented by X and Z? Well, let's see. What do we have here? This is Fe as a solid. That's an element. The next one is a compound. This and these two over here are mixtures. So what category of matter includes elements and compounds? Well, substances. X is a substance and Z is a mixture. All right, number 39. Based on table G, which sample, when added to 100 grams of water and thoroughly stirred, produces a heterogeneous mixture? So I don't love this question, but let's talk a little bit about it. Okay, so on table G, which just really quickly, this is table G, right? On table G, when it is on the line, right, it is saturated. And saturated is a homogeneous mixture. Okay. When it is below the line, right, it is unsaturated, but all of it has dissolved. So it is still going to be homogeneous, right? If it is above the line, right, it is super saturated, which means not all of it is dissolved, it has too much in it. So that is where we're going to be looking for heterogeneous. The other way we could approach it, right, is the one of the things is not like the others. So let's look at kind of both at the same time, all right? And hopefully it'll make sense for you at the end. But again, when it comes down to it, this is one question, so I wouldn't stress too much about it. It does say we have 100 grams of water, and it does say we have 20 degrees Celsius, okay? And we're comparing two different substances. So I'm going to first look at Ki, all right? Ki is way up here, all right? 20 degrees Celsius is literally right here, so it is the second line over. So it doesn't matter if I have less than, like 145 grams, it is going to be unsaturated. So for both of these situations for Ki, they are both unsaturated, right? Which means everything dissolved, okay? So that should tell me at this point that I'm definitely not looking for something that is unsaturated, all right? So now I need to find KCl, and I still need to compare 20 grams and 80 grams. So let's go down here. Here's again 20 degrees Celsius, 20 grams, okay, and 80 grams. KCl's line is right here. So where it crosses 20 is right there. So you can see that 20 grams is under, it's unsaturated, but this one is above, it is super saturated. So my correct answer is going to be this one, the one that gets me on top. That is different. All the other ones were unsaturated. So again, the one of these things is not like the others. Okay. How many milliliters of 1 molar HCl aqueous must be diluted with water to make exactly 500 milliliters of 0.1 molar HCl aqueous? All right, what I should realize first is that this kind of really doesn't make any sense. All right, that's saying I need to use a lot of the concentrated one to make a less concentrated one. That doesn't make any sense. Okay, so but you should realize that concentration times volume, that is going to be consistent. All right, so the concentration of one, right, times the volume of the other should equal the concentration times the volume, okay? So 1, right, for that's this molarity times something equals 500 times 0.1. So let's just do that. Let's just do 500 times 0.1. That gives us 50. So 1 times 50. So this one is going to be 50 milliliters. Again, don't love 39 and 40 as questions, but you have to work with what you have. Which two particle diagrams represent two different phases of the same compound only? Okay, so let's see. Let's look for differences. This is a compound, but this is an element. Okay, so that's wrong. Okay. Although these are reversed, this is so this is one compound, right? Let's look at this. This is one compound. This is two different. This again is element and compound. So I don't want this. So which two particle diagrams represent two different phases of the same compound only? It is going to be B and D. A sample of KCl is dissolved in water to form KCl aqueous. When the water in the KCl aqueous is completely evaporated, KCl solid remains. Which statement describes a property of the KCl solid after the water evaporated? Well, the properties don't change. So the melting point is unchanged. You're just physically separating them. That's it. Which statement describes ice and liquid water in a stoppered flask at 0 degrees Celsius at equilibrium? So what do you remember about equilibrium? Rates are equal. Also, concentrations are constant, okay, depending what they ask about. So the rate has to be equal. So the one that says rates are equal is right here. Rates are equal. Given this equation representing a system at equilibrium in a sealed container, when heat is added to the system. So where's heat represented? By kilojoules. So when heat is added, what happens? I need to use it up. In order to use it up, I have to move to the opposite side of the equation. So I move this way. As I move that way, I start to use this up. I start to use this up. I start to use this up, which was the whole reason I need to use up that excess. And I'm going to make this, okay? So let's look for something that matches. So what happens to the concentration of N2? Well, it goes down. And what happens to NO? It increases. You could even get this to a 50-50 if you remembered that things on the opposite sides of the equation have to do opposite things. Okay, so that could help you. All right, given this potential energy diagram for reaction, which numbered interval represents the activation energy? Now, if it doesn't say different, it means activation energy for the forward reaction. Activation energy takes you from reactants to the top of the activated complex. So that is number 1. Okay. Given the formula representing a compound, what is the chemical name for the compound? Well, notice these all say pent. So the number of carbons in the chain isn't going to help me. Okay. So what is different? There, some end in ane and some end in ene. So let's go to table Q really briefly. And you will see that when it ends in ane, it has all single bonds. When it ends in ene, it has a double bond. So what do I see here? Well, I see all single bonds. So that means I can eliminate the enes. Okay. Now I need to figure out what is the correct name. So I need an address, and an address indicates what carbon is attached to. So I could number them like this. That's carbon 1, that's carbon 2, there's 3, there's 4, and there's 5, okay? Or I could number them in reverse, okay? So in that case, they would be numbered like this. This carbon would be 5, this would be 4, 3, 2, and 1. Because remember, this is not really stuck on paper. In real life, I can rotate the thing, right? I can move it. So when I number, okay, so here is what I'm looking for, the chloro, that's the Cl. Look at what carbon it's attached to. It's either, I could name it, it's attached to 4 or 2. But the rule is I use the lowest number possible, so it's going to be 2-chloropentane, okay? Which formula represents a saturated organic compound? So on this table, alkanes are the only ones that are saturated. And you see their chemical formula, whereas you take the number of carbons, double it, and then add 2 more. So let's look. How many carbons do you have? 2. What's double 2? 4. Do I have 4 hydrogens? No, I got less. That's wrong. 2 carbons, double it, 4. Do I have 4 hydrogens? Yes, that's an alkene. How many carbons do I have? 3. Double it, 6. Do I have 6 hydrogens? No, I have less, alkyne. How many carbons do I have? 3. Double it, 6. Do I have 6 hydrogens? Nope, I have more. Finally, I get an alkane. Okay. the compounds CH3, CH2, CH2OH, and CH3O, CH2, CH3 have different what? Well, if I count, they have 3 carbons. So they do not have different numbers of carbons. Hydrogens, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. They have the same number of hydrogens. And they both have 1 oxygen, so they have the same molecular masses. So they have different functional groups. Where else could I find that information? If I went to reference table R, an OH versus an O in the middle, it's the difference between an ether and an alcohol. Okay. Last 2 multiple choice questions. All right, here's a voltaic. So notice it says voltaic cell. It also has a voltmeter in the picture. And, well, let's use table J for a moment and let's get some labeling done. So what 2 do I have? Magnesium and nickel. So on table J, magnesium and nickel. So magnesium is higher, right? So that means magnesium is the negative electrode. That's always true, right? And since this is a voltaic cell, the higher one is always the anode. And because anox, that's where oxidation occurs, right? So that is losing electrons. And on this side, that means nickel would have the positive charge. It would be the cathode. And red cat, it would have reduction. It would be gaining electrons, right? So let's look at this. It says, which describes the direction of electron flow. Well, first of all, do electrons flow through the wire or the salt bridge? I can get this to a 50-50. They absolutely go through the wire, okay? And which way do they go? 100% of the time from anode to cathode. So in this case, that means from magnesium through the wire to nickel. All right, last multiple choice. Given the equation representing a reaction at equilibrium, according to one acid-base theory, which means it's not Arrhenius, it's Bronsted-Lowry, which pair are H plus donors? Okay, so let's see if we can follow where the H went. So I started as NH3 and I ended with NH4. So that means an H went this way. So H2O is one of the donors. Okay, so I can eliminate those 2. So what's happening on the other side? On the other side, I start as NH4 and end as NH3. So that means this side, the H went this way. So my correct answer is NH4 and H2O. And finally, we have finished all the multiple choice. Whew. All right, multiple choice is done. We are moving on to part B2. And B2 is like the simpler questions where you have to actually write an answer. And here is where we're going to need the answer booklet. And so each question is going to kind of give you a clue as to, is it a short answer or a little bit longer? So I can tell already that 51 is a short answer. So let's look. Identify a metal from table J. Okay, this is simple. Look at table J. That is less active than silver. All right, so here is the reference table. Let's go to table J. All right, let's find silver. And silver is right here. Okay, now how am I going to identify a metal that is less active? Well, look, there is even literal most active and least active. So something less active than silver, well, it is really simple because it can only be one thing, right? There's only one thing underneath silver, and that is AU, right? So here's silver, one thing underneath. Do you know what AU is? Well, it's gold. So in the answer booklet, I could write gold or AU. That's the answer. Okay, so again, that's 51. Now let's move on. Base your answers to 52 through 54 on the information below and on your knowledge of chemistry. It almost always says that, which means you're going to have to pull some stuff from your brain.
Fluorine, chlorine, bromine, and iodine are located in group 17 and are called halogens. State in terms of, oh, here's an in terms of question. That means my answer better say the word electrons, okay? Why these halogens have similar chemical properties. Okay, so I think I'm going to need the periodic table. So here we go. Let's zoom in a little bit as we're going to focus on the halogens, right? So let's go over here, group 17. Zoom in a little more. I can see them even better. All right, so here we have halogens here in group 17. In terms of electrons, why do they have similar properties? Well, they don't have the same number of electrons because this is atomic number and the number of electrons in an atom. So fluorine has 9, chlorine has 17, bromine has 35, and so on. What do they have the same? Look at this last number. And that is what determines their chemical properties. So what is it that's the same? They have the same number of valence electrons. Let me put the E in here. Okay. What else could I say? The halogens all have 7 valence electrons. Okay. Both of those answers are correct. I mention electrons and I talk about why they have similar properties. Compare the radius of a chlorine atom to the radius of a Cl negative ion, which a Cl negative ion is a chloride ion. Okay, so if the atom is neutral and the chloride ion is negative, okay, one is going to be bigger. That's literally what compare means. Either they're the same size or one is bigger. Well, in order to go from a chlorine atom to a chloride ion is going to gain 1 electron. And when it gains an electron, it's going to end up larger. Okay, so a chlorine atom is smaller than a chloride ion, right? Or I could say a chloride ion is larger than a chloride atom. All right. What I have to be careful about is I don't want to say the ion is larger because it gained an electron, because that's not true. The atom gained the electron. Okay. So you could say a chlorine ion is larger because it has 1 more electron. That would work as well. Okay. And the last one in this section, in the space in your answer booklet, draw a Lewis electron dot diagram for an atom of fluorine in the ground state. Okay, so let's scroll down a little bit. You can see I just have blank space. Remember that fluorine had 7 valence electrons, and I'm drawing the atom, not the ion. I'm double checking, okay? So what do I do to draw a Lewis electron dot diagram? I write the symbol for the element in the center, and then I am going to put dots. I'm just going to make this thicker so I can do the dots easier. 1 dot for each valence electron. So 1, 2, 3, 4, 5, 6, 7. There we go. There is the Lewis electron dot diagram for a fluorine atom. 55 through 57. A sample of helium gas in a sealed rigid container is at 240 Kelvin and 120 kilopascals. the temperature is increased to 360 Kelvin. All right, 55. State the number of significant figures to which the given pressure is expressed. Okay, so which one of these is pressure? If you totally blank and forget, okay, I'm going to show you where to go. So here, table D, selected units, and look and find the one that is pressure. Okay, so the pressure is right here. Significant figures. How do we determine significant figures? Okay, well, I'll just give you a quick example here. So if I have this number right here and it has a decimal point, we begin counting on the left side and we start at the first digit that is not a 0, go this way and count everything. So that would have 4. If it was this, no decimal, then we start counting on the right side, go this way, look for the first number that is not a 0, and count everything. So that would have 1. So if we look at this pressure, it has a decimal point, right? So I'm going to start here and count everything. So it will be a simple answer, 3. Right? Or I could write the number 3. Right? That's also acceptable. All right. I bet you I'm going to do some solving for 56. Let's see. Determine the pressure of helium at 360 Kelvin. Okay. So you should recognize when I've got temperature and pressure and a gas, then I have something I should be looking for. Do you know what it is? All the way at the back of the reference table, the combined gas law. All right. So in my answer booklet, because I have this space, oops, I forgot that's so enlarged. Let's still use it, but let's bring it down to a reasonable. All right. So P1 V1 over T1 equals P2 V2 over T2. All right, so let's see what we got. So we have a temperature, we have a pressure, we have a temperature, and we're looking for a pressure. And it says this, a sealed rigid container. So guess what that means? Ugh, I love it. That means volume doesn't matter, so I can get rid of it from this formula. So then I'm just going to plug in what I have left. So P1 and T1. So what pressure did we start with? 120. What temperature did we start with? 240. Equals, what pressure did we end with? Oh, that's what I'm finding. So keep that P2. And what temperature did we end with? 360. Okay, so I'm going to just, because I'm math sensical, I'm going to point something out here just because sometimes it helps to determine logic. I can tell very quickly that 120 is half of 240. So on this side, whatever this number is, it should be half of 360. Okay? If you are not math sensical, you may not have noticed that. So what you would do is cross multiply. So you would take 120, right, times 360 equals 240 times P2. All right, so then you would get your calculator and do 120 times 360 and you would get 43,200 equals 240 P2. Divide both sides by 240. Let's bring our calculator back up and divide that number divided by 240 equals 180. So 180 equals P2. Go back to the question. What were my original units for pressure? kPa. So my units here are also kPa. Now remember what I said if you were math sensical? What's half of 360? Yeah, 180. Okay. So I could have got the answer that way, but this is a great check. Okay. And if you aren't sure, might as well do it and get it right. Okay. But this work is not for question 57. So I just have to make a note of that. I could do this scrap work here, or I could do the scrap work here, right? But I have to make sure that I have room to answer number 57 in this space. Okay. Show a numerical setup for converting 120 kPa to atmospheres. I actually love this question. It's relatively easy. All right, so what I'm going to do is just clear this space right here so I have room to do that. Okay. What I'm going to need in order to convert kPa to atmospheres is use what I have in table A. Okay. So I'm going to go all the way back from table T to table A. And you could see that I have values for standard pressure. So I'm going to use that as a ratio. So again, I'm going to use this and set up a proportion. What do I mean? I'm going to write what it literally gives me. 101.3 kPa, right, is the same as 1 atmosphere. Okay. But I don't have 101.3 kPa. What do I have? 120. So I'm going to put 120 kPa up here and over X or question mark or whatever. And that is how I solve for it. And you don't have to do anything else. Like I could cross multiply to set it up, but I don't need to. Okay, that's it. I can just leave it like that. All right, we are on to 58 and 59. So I've got a table, I've got a graph. So let's just go to the question because I don't even know what I have to look at. So based on the graph, okay, got to look at the graph. Determine the boiling point of butanal at standard pressure. So let's go up and it says that butanal right here has a molar mass of 72.1, right? So the molar mass, right? Okay, if it is 72.1, okay, so it's like this is 70, this is 80, that is 75. 72.1 is a little bit closer to 70, but it's going to be between these two, almost halfway, but not quite. So I'm going to go up and where do I think it would be? Well, if I look at this line that's going up like this, right, I'm guessing it's going to be about here. Okay, so what is that in terms of boiling point? Well, this is 350, this is 360, so like 355. Okay, so I'm going to write that. So 355. Now, if you're curious, what did the Regents exam accept for this? Anywhere from 340 to 360 Kelvin. You could have had 340, 341, anything all the way up until exactly 360. So a huge range that you were given for that. Okay. All right, next question. Determine the mass of 3 moles of propanol using the molar mass given in the table. All right, so what does it say for propanol's molar mass is 58.1. Okay, so let's use the space down here. So 58.1 grams per mole is the molar mass. Okay, what else do I know? I have 3.00 moles and I want to find grams mass. Can you guess it's probably a formula? So I'm going to go all the way to table T again. And right here, So moles is given mass over gram formula mass. So let's set that up. So moles, right? I know moles is what? 3. And I don't have to put those zeros anymore. Equals mass. Well, that's what I'm trying to find. So I'm just going to label it G, right, for mass. And it's going to be over the molar mass, which I know is 58.1. Okay. And then that's over like that. So how do I solve for this? Well, here's my tip. You do much better doing it this way, at least in my experience. Put this over 1 and then cross multiply, right? So when I do that, I get 1 times the grams, which is just grams, equals 3 times 58.1. Well, then that's easy peasy, right? Grams equals, pull up the calculator, 3 times 58.1. 3 times 58.1 equals 174.3. All right, 174.3, and that's going to be grams. And guess what? I do not have to round it. I can leave it exactly like this. Do not have to. Because it did not mention anything about significant figures. So that's what I'm going to do. I'm just going to write exactly what I had. 4.3. Now, in case you're wondering what was the Regents accepting, the Regents was accepting from 173.997 to 174.3. Okay? They did offer a range. Okay? I'm guessing in case somebody didn't actually use the molar mass from the table and self-calculated it, even though it told you not to do that. But you could have rounded it then to 174, would have totally been fine. But again, it's always acceptable, unless it says significant figures, to simply write what the calculator gave you. Okay? All right, 60 to 62. All right, so I'm going to skip the reading for now. Maybe I don't even need it. Number 60, describe the change in potential energy of the water molecules that vaporize during boiling. Okay, so it's saying what happens to the potential energy of water as they vaporize. So as it goes this way, what happens to potential energy? Well, in a liquid, the particles are real close together, although they can slide past each other. In a gas, the particles are far apart and moving rapidly, so potential energy increases. Kinetic energy increases and potential energy increases. But this is just asking about potential. So, okay, as the water molecules vaporize, the potential energy increases. What else could you say instead? The water vapor has more potential energy, right? You could simply say the potential energy increases. Okay, those would all be acceptable answers. 61. Compare the entropy. Again, with a compare question, it's either going to be the same, greater, or less. That's it. So you should know that. Compare the entropy. Well, first of all, do you remember what entropy is? Entropy means disorder or randomness. Okay, so let's compare the entropy of the water as a liquid to water as a gas. Okay, so again, what do we know? That as we go from liquid to gas, the entropy, the disorder, increases. So the water vapor has more entropy. Okay, so what else could I say? The liquid water has less entropy. Could say the gas has more disorder and a higher entropy. We don't want to say all three of those answers, but one, That's it. All right. Number 62. Determine the mass of liquid water that vaporizes if 7,700 joules of energy is absorbed by the water at 100 degrees Celsius. Okay, sounds like a formula, right? So what formula is it? Well, it's one of these. Okay, let's go back to the question. Is the temperature changing? Nope. If the temperature is not changing, this is not an answer. Okay, it is talking about vaporizing. So obviously, I need the formula that has heat of vaporization. Okay, so what I need is Q equals mHV, right? I know the Q, right? What is the Q? 7,700 joules. And do I know the mass? Nope, that's what I'm trying to find. Equals mass times, well, this question doesn't give me HV. So it's a reference table part, right? So right here, heat of vaporization, 2,260 joules, okay? Times 2,260 joules. How do I solve for M? I need to divide both sides by what? I need to divide both sides by 2,260. On this side as well, divide this side by 2,260. So then I open up my calculator. Okay, ready? And I need to do 7,700 divided by 2,260. Okay? And I'm going to get this 3.40707. Now, I could literally just write all of that. But I don't need to write that many digits. Okay? I could, but I'm not going to. So I'm just going to write 3.407. Okay? As my answer. So I'm going to write 3.407. So you may say, well, what did the Regents accept? Okay? Well, the Regents accepted anywhere from 3.4 to 3.41, but the number of digits didn't matter. So this answer I gave is in between those, right? So perfectly acceptable and a correct answer. All right, I am ready to finish up part B2, all right, with these last three questions. State the number of neutrons in an atom of tritium. Well, it tells me right here that it's this, okay? So hydrogen 3. So hydrogen 3. Where do I put the 3? If you space out and forget, there's help. Where? Table N. Ready? Look, here's hydrogen 3. Look at where they wrote the 3. Brilliant. Okay, so I put the 3 up here. In order to find neutrons, so this is mass number. In order to find neutrons, I also need this bottom number, which is atomic number or charge. So that is going to come from the periodic table, okay? And where am I going to find the atomic number? So I need to find hydrogen. I mean, reality, you should know hydrogen. It's the first element on the periodic table. Its atomic number is 1. So how do I find neutrons? I simply do this math problem. So how many is it? You're right. It is 2. You could also write the word 2. Oh, look, 64 is brilliant. I love this. Let's just make sure what it says. Complete the nuclear equation in your answer booklet for the decay of tritium by writing a notation for the missing nuclide. Okay, so I need to find out what's missing. Remember how we did these before? We need to solve for the top number and solve for the bottom number. And for the arrow, it's an equal sign. So 3 equals 0 plus x. This should be obvious, right? 3 is x. Let's solve for the bottom number. Here's where you have to be careful because there is a negative involved. So 1 equals -1 plus x. I got to add 1 to both sides, right, to get rid of that. And I'm going to get 2 equals X. So I'm going to end up having a 3 on the top and a 2 on the bottom, but I need number, and a symbol, right? How do I find the symbol? Well, I go to the periodic table, and which one has atomic number 2? That would be helium. Okay, so right there. 3 on top, 2 on the bottom, helium. Okay. And lastly, for B2, based on table N, identify a nuclide that has the same decay mode as tritium, but has a longer half-life. Okay, so I got to find tritium. I was already here. It has this. Beta. What if you forgot? Right here, right? Beta. So I need to find something that has the same decay mode, but a longer half-life. So this is years. All right, so let's go here. Well, that's shorter days. Oh, that's definitely longer. So carbon-14 is a possibility, right? Carbon-14. Whether I wrote it with the, I could have written it like this, 14 carbon, right? What other acceptable answers are there? There's more than just carbon-14. So what about this one? Is that longer? Nope. About this one, is that one longer? Yes. So cesium-137 is an acceptable answer. All right, let's see. Are there any more? Again, you only had to put one, right? So keep going past this one. Nope. 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 Close, but nope. 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 Yes. Strontium-90. Okay, so strontium-90 always also works. And let's see, are there any more? Well, let's check. Only a few more left on the list. Oh yes, technetium-99. The rest are alpha. So technetium-99 is the last one. And so all of those are acceptable. You had to pick one. And you could have written any of them like this or like this, whatever your preference was. Okay? End of B2. All right, we are on to part C, the final questions on the exam, going up through 85. And these are technically the harder written ones, although, you know, they can be a little bit debatable. All right, so we have some reading here and an equation, but let's skip and go straight to the question. Balance the equation in your answer booklet for the production of phosphoric acid using the smallest whole number coefficients. All right, so let's look at what we have. We have this equation, and I'm just going to start balancing it and see what happens. Well, I have 4 phosphorus here and only 1 here. So that means I would need 4 phosphorus, right? Okay. Well, oxygen, see how oxygen is in 2 things here? So I'm going to hold off on oxygen, and I'm going to try to balance hydrogen and see if that works everything out. For hydrogen, 4 times 3 is 12. So I need 12 hydrogens on this side. How do I get 12 hydrogens? I would multiply this by 6. So phosphorus is balanced and hydrogen is balanced. Let's check oxygen. So oxygen, I have 10 right here, right? How many do I have here? 6. So that makes 16 total oxygens. And over here, I have 4 times 4, which is, oh, brilliant, 16. So this is done. I can write it exactly like this and be finished, or I could put a 1 in front of here. Either is acceptable. Write the empirical formula of the solid reactant in the equation. So reactants, here's the arrow. Reactants are over here. Here's the solid. Empirical means reduce it, right? So you can divide 4 and 10 by something. By what? By 2. So I'm going to get P2O5. Okay? So in the answer booklet is where I have to write it. I could write it there, but that doesn't count. P2O5. All right, number 68. Show a numerical setup. Means don't solve it, just set it up. So pick a formula or set up a ratio and put in the numbers. For calculating the percent composition by mass of phosphorus in this, and it gives me the formula mass. So let's go look at the table T and get the formula for percent composition. It is mass of part over mass of whole times 100. So I am just going to write that right here, okay? So the percent, right, the percent equals part over, well, I'll do it this way, part times 100, and then we'll put whole underneath, right? And then I'll just add a line to make it clear. Part over whole times 100. So they gave me the formula mass. Well, is formula mass the whole thing? Yes. So 283.89. So that goes in place of the whole. Okay. So I'll just write this over here. So the whole equals 283.89 U. So what is the part? Well, they said for phosphorus, and the formula has 4 phosphorus, right? So let's go back over here. The percent, okay, is going to equal 4 times the mass of phosphorus, right, times 100, and then it's going to be divided by 283.89 because that's the whole thing. Right, let's put our line here so we know what we're doing. Oops. But I am not finished yet because I need to put what it is for P, because I can't just solve this, right? So I need to have all the numbers that I need in order to solve it. So I need to go back to the periodic table and find the atomic mass of phosphorus, which is 31, right? Because it's going to round up, because usually we're rounding to 1 decimal point, but we need to round it up, so it's 31. So now when I put this in, I will be finished setting it up. So again, percent equals 4 times 31, right, times 100, and then on the bottom we have the whole thing, the formula mass, which they were kind and gave it to us, so we didn't even have to do that math, and I just have to make sure that this is like this, and that's it. I actually don't need to multiply the 4 times the 31. I don't need to do any of the math. I just have to make sure that I have all the information I need to solve it, and I do, so I'm finished. Okay. And number 69, determine the oxidation state of phosphorus in phosphoric acid. So it told me that phosphoric acid is what I produced. If you wanted to double check, you could go to table K and see that, yes, indeed, that is phosphoric acid. So the formula for phosphoric acid is H3PO4. And I want to find the oxidation state of phosphorus. Okay. I like to just set these up as an equation. First, what I'll point out is that there's no charge up here. So the whole thing has to equal 0. So what does that mean? That means 3 H's plus 1 phosphorus plus 4 oxygens. I'm going to write oxygens. So be careful that that's not a 0, right? Equals 0. So see how it looks a little different? So I need the oxidation state for hydrogen. And unless hydrogen is with a metal, it's always the +1. Okay, so 3 times +1 plus phosphorus is what I'm solving for, plus 4 times what is oxygen. Go on this side of the table, -2 times -2 equals 0. All right, so that's 3 plus phosphorus plus -8 equals 0. Combine those like terms. 3 plus -8 is -5 plus phosphorus equals 0. Add 5 to both sides, right? So phosphorus equals, and remember for oxidation states, we need the sign no matter what. So plus 5. So my answer here, plus 5. Okay. All right, we finished that first section. Now we are on this one. Again, I have some reading and a formula, but let's skip. State the solubility of limestone in water. Well, okay. So it must tell me what limestone is. All right. So calcium oxide, also known as lime, is an important industrial chemical. Lime can be obtained by the heating of limestone, which is mainly calcium carbonate. Okay. So in order to determine the solubility of limestone, I need to find the solubility of calcium carbonate. How do I determine solubility? Well, that would be, remember, table F, okay? So it is calcium carbonate. So here's carbonate. Carbonate's rule is insoluble unless it is with group 1. Is calcium in group 1? No, it is in group 2, okay? So it doesn't make it break its rule, so that means, and it's not NH4. So calcium carbonate is going to be what? Insoluble. All right, insoluble. And now, number 71. State evidence from the equation that the reaction to form lime is endothermic. Well, endothermic means energy or heat is absorbed. And look at where heat is. So what evidence is it from the equation? That heat is a reactant. Okay? So that is one way I could say it, right? Heat is a reactant in the equation. That's evidence from the equation. What else can I say? Heat must be added to the reaction, right? I could also say heat is on the left side of the equation. All of those prove it is endothermic. Identify the noble gas that has atoms in the ground state with the same electron configuration as the calcium ion in the ground state in this. Okay, that's a lot. So let's just pause for a moment. Okay. So what I need to do is figure out how many valence electrons calcium has. But let's go to the periodic table. Here's calcium. It has 20 electrons total. Its oxidation state is +2, which means what? It will lose 2 electrons. When it loses 2 electrons, it no longer has 20. How many does it have? 18. And then look at this. What noble gas has 18? Argon. All right, so our answer is argon. I know there was a lot of words in the question for not really a hard question. And state the type of bonding, chemical bonding in a sample of calcium oxide. Well, it's a metal and a nonmetal. What kind of bonding is that? Ionic. What if it was 2 nonmetals? Covalent, right? And if they had asked for this, because it has something from table E, the carbonate ion, it would have both ionic and covalent. But they didn't ask me that. 74 and 75. Again, I'm skipping the reading until I need it, and I'm going to go here. Compare the number of moles of H plus aqueous ions to the number of moles of OH negative aqueous ions in the titration mixture when the HCl is exactly neutralized by the KOH. So for this question, I literally don't need the reading. Compare is what? Either the same, greater, or less. Those are the only answers. So when it is exactly neutralized, the pH is 7, which means the H plus and OH negative are equal. Just know that, right? So the number of moles of hydrogen ions is equal to the number of moles of hydroxide ions. I could say concentration of H plus is equal to the concentration of OH negative. Okay. What else could I say? The number of H plus ions is equal to the number of OH negative ions. You don't say all of those. Pick one as the way you want to say it. Number 75, determine the concentration of the HCl aqueous solution using the titration data. Okay, so now I need to go to the reading. All right, now it says using the titration data. So when you look at table T, there's a titration formula. Okay, so I know what I'm using here is MAVA equals MBVB. That's my formula. Okay, so I have 20 milliliters of HCl. That's VA. Okay, and of an unknown concentration. So I don't know MA. So I'm going to keep MA. What was VA again? It was 20 equals MB and VB. The solution is titrated with, here's the concentration of the base, and that is how much was added. So MB is 0.10 and VB is 42 milliliters. So I'm going to take MA 20, leave that, multiply 0.10 times 42, which is going to be 4.2. Okay, then I'm going to do what? Divide both sides by 20, right? So I'm going to divide both sides by 20. And that is going to give me an MA answer. Okay, so let's pull up our calculator. All right, so I'm just going to show you that 0.1 times 42 is 4.2. Divided by 20 is 0.21 molar. So there's my answer, 0.21. And they already have the units, right? So what was acceptable on the exam for the Regents? Anywhere from 0.2 to 0.21. Okay, so you could have rounded it to 0.2, or you had any value as long as it was in between those two numbers. All right. Okay. Identify, again, I've got a structural formula, skip it. Identify the element in these four compounds that makes them organic compounds. Well, I don't even need to know which four compounds they are. What makes something organic? What element? Come on. This is basic. You better know it. Carbon, right? All right. Number 77. Write the names of the two organic compounds detected on the comet that are isomers of each other. Okay. So I have 4 that are up here, right? I have methyl isocyanate, propanone, propanal, and ethanamide. And it says the structural formula for methyl isocyanate is shown below. Okay, so first of all, do you see this right here? It has nitrogen in it. Let's go to table R. So first of all, that's what I need. Okay, so I have propanone, propanal, and then I've got this, which they gave me, right? And then ethanamide. So let's look up propanone. Ends with this, so it's a ketone, so it has this in it, right? And then we have propanal, right? Anal, so it's an aldehyde, it has this. And then we have ethanamide. So first of all, eth, what does that mean? It has how many carbons? 2, right? So it has 2 carbons. And so that would not be the same because prop and prop, those both have 3. So ethanamide. Let's look at what an amide is down here. It has a C double bond O with nitrogen and hydrogen. Okay. But look at this. That's got a double bond between the nitrogen and the carbon. Is that what an amide has? It does not. So if there's a double bond in only one of them, they can't be isomers. So the 2 that are going to be isomers are going to be propanone and propanal. All right. And let's move on. Oh, we're so close. Look at, we're getting to the 80s. So I have this diagram here. And I do have some reading and I have a diagram, but I'm going to skip to the question. Using the results of the student's investigation, state evidence that zinc metal is more active than copper metal. Okay, so here's the results right here. So let's look at the evidence. So here is when I used zinc metal down this column. And here is when they used copper metal down here. And then I need this key. So metal strip with no change, metal strip that appears dark, which means it reacted. So if we look at this, how many times did copper react? 0. How many times did zinc react? 2. So why is zinc more active than copper? Because zinc reacted with 2 of the solutions and copper reacted with none. Okay, so zinc reacted with 2 of the solutions and copper did not react with any. Okay, what else could you say? Well, you could say zinc is dark in 2 of the solutions and copper is not dark in any of the solutions. What else could you say instead? Well, you could say copper does not react at all, but zinc reacts twice. Different versions of the same answer, right? Okay. Now we're on 79. Compare. What do we know about compare? It's either equal, greater, or less. So compare the number of electrons lost by the magnesium placed in the zinc solution to the number of electrons gained by the zinc aqueous. Well, this is like literally redox. What is true? The number of electrons lost is equal to the number of electrons gained. Okay? Right? That's it. The number of electrons lost is equal to the number of electrons gained. You could say it in different words, but you need to say that they're equal. Okay? Write a balanced half reaction equation for the reduction of the copper ions. Okay. So if it says the reduction of the copper ions, that means here's the copper ion and it is going through reduction. Right? What does reduction mean? Ger, which means it gains electrons. And what is it going to change into? This copper metal. So I'm just going to put the copper on both sides just so you could see what I'm talking about. Okay, so I'm going to write the charge in myself, but I have copper on this side, and on the other side I have the copper metal. So first let me move this over, and I'm going to write in the charge. So 2 plus. Oh, it looks a little bit like a Z, but forgive it, it's a 2. Okay, remember that both sides of the equation have to be balanced, and this is a 0 and that's a positive 2, and that is definitely not balanced. So changing from a +2 to a 0 is 2 electrons. So I need to add them, and here's the memory trick. So GR is reduction, reactant R. So the electrons go on the reactant side. And for electrons, you absolutely have to write that negative sign. And that's -2 and a +2 equals 0 on this side. Brilliant. Done. Okay, one more question here. State why the student was instructed to clean the surface of the metal strips with sandpaper before placing each strip into an aqueous metal ion solution. Okay, well, you know that if you leave metal alone, it's going to react with the air. So using the sandpaper, removed any of the tarnish, right? I spelled tarnish wrong. Okay. Using the sandpaper, exposed the surface of the metal for the reaction. Okay. Using the sandpaper, cleaned off any tarnish or reacted metal so the reaction can proceed. All right, or something along those lines. Okay, and we are almost done. Look at this. All right, let's move on. 82 and 83. Explain, again, I have this reading, but if you notice, this isn't like English. Most of the time you literally don't need it, so I'm going to skip it. Explain in terms of intermolecular forces why tetrachloroethane has a higher boiling point than tetrachloromethane. Well, I got to talk about intermolecular forces. Why does something have a higher boiling point? Literally, just know it. So, tetrachloroethane has a higher boiling point because it has stronger intermolecular forces. Strong forces hold the particles tighter and make it harder for it to boil. That's it. Higher boiling point means stronger intermolecular forces. Okay, know it. Okay. Draw a structural formula for 1-bromopropane. Okay, here's our space. Are you ready? So 1-bromopropane. So I can get a little bit of a hint from here. Prop is 3 carbons. So start with that. All right. Carbon bonded to carbon bonded to carbon. 1-bromo. So right here, it's a halide. Look at what I write for bromo. So I need to put a BR, well, like this. I need to put this somewhere. Where do I put it? Well, it told me where, on carbon number 1. So I'll put it right here. It doesn't matter which spot on carbon number 1 you put it, but it's got to be on carbon number 1. And now I need to add the remaining lines for the hydrogens. And I don't have to write the hydrogens. You can, but you don't need to. What you need to make sure is that every carbon has 4 bonds around it. And that's it. That is complete for 1 bromopropane. Look at this, 2 questions left. Whew, we're almost there. Okay, again, reading, equation, go to the question. Compare, oh, brilliant, what do I know? The same, greater, or less, that's it. Compare the energy released per gram of reactant during this reaction to the energy released per gram of reactant in a chemical reaction. Well, what kind of reaction is this? Is nuclear. And the nuclear reaction always produces more energy. So the nuclear reaction produces more energy than the chemical reaction. Like a whole lot more. Remember, a nuclear reaction is going to convert some mass into energy. Okay? So you could say the nuclear reaction releases more energy, or you could say the reverse and say the chemical reaction releases less energy. Those would all work. Okay. And here we go. Determine the time required for an 8 milligram sample of strontium-90 to decay until only 2 milligrams of the sample remains unchanged. Okay, so I'm starting with 8 milligrams. And then here's a half-life. Half-life number 1. So I have half of that. That's 4. I need to get to 2, so go again. After another half-life, that's half-life number 2. I am at 2. Perfect. But now I need to know time. It doesn't tell me time anywhere here. So, oh, table N, right? So scroll back here to table N. And what substance did I have? Strontium-90. So find strontium-90. And here is its half-life. So its half-life is 29.1 years. But I didn't have it go through one half-life. It had to go through 2 half-lives. And this one lasted 29.1 years. And this one lasted 29.1 years. So how long is that altogether? 29.1 plus 29.1, which is 58.2 years. And voila, we finished it. We did it. All 85 questions. You got this.